Something orbits Saturn that looks like it was built, not born. It is smaller than most cities. Its entire mass is roughly equal to the water filling one of Earth's Great Lakes. And when NASA's Cassini spacecraft flew close enough to photograph it, the image it sent back silenced entire rooms of planetary scientists. Atlas, one of Saturn's innermost moons, looks almost exactly like a flying saucer. A smooth, flattened disk with a sharp equatorial ridge that circles its entire body like a belt made of frozen dust. It does not look natural. It does not look like any moon you have ever seen. But it is real. And it is natural. And the explanation for how the solar system built something that looks engineered is stranger and more beautiful than almost anyone expects. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. On April 12th, 2017, a spacecraft that had been circling Saturn for nearly 13 years aimed its cameras at something most people had never heard of. The target was not Titan, Saturn's giant haze-covered moon. It was not Enceladus, with its erupting geysers of salt water. It was a tiny body orbiting just beyond the outermost bright ring of the planet. A body so small that in most photographs of Saturn it would not even appear as a single pixel. The spacecraft was Cassini. The target was a moon called Atlas. And the images that came back that day were among the most unsettling photographs ever returned from the outer solar system. Atlas did not look like a moon. It looked like a disk. A flattened, pale, eerily symmetrical object with a sharp ridge running around its entire midsection, tapering to a thin edge like the rim of a ceramic plate. From certain angles, it resembled a classic flying saucer, the kind sketched on the covers of 1950s pulp science fiction magazines. From other angles, it looked like a lens, or a hamburger, or a coin that had been pinched along its edges. The equatorial ridge was smooth. The polar regions above and below it were rougher, pitted, more obviously battered by time. But that central band was clean and geometric, wrapping the entire body in a single unbroken line like a belt cinched around the waist of the moon. No matter how you rotated the image, the conclusion was inescapable. This didn't look like something that belonged in nature. It looked engineered. It looked designed. It looked, to put it plainly, like something that had been built. Cassini took the images during a flyby that brought it within roughly 11,000 kilometers of Atlas at closest approach. At that distance, the resolution reached approximately 250 meters per pixel, meaning each tiny square in the image represented a patch of surface about 2.5 football fields across. That was sharp enough to see texture. Sharp enough to see the contrast between the smooth equatorial material and the rougher terrain at higher latitudes. Sharp enough to confirm that the shape was not an illusion of low resolution or a trick of shadow. The flying saucer profile was real. The geometry was written into the body itself. The reaction among planetary scientists was not shock, exactly. Researchers who had been studying Saturn's small moons had known for years that Atlas was oddly shaped. Earlier Cassini images, captured from much greater distances across the preceding decade, had shown a flattened silhouette. A study published in the journal Science back in 2007 had already described the equatorial ridge and proposed that it was linked to ring particle accretion. But those earlier views were grainy. They left room for ambiguity. The 2017 flyby images eliminated that ambiguity entirely. Atlas was not roughly saucer-shaped. It was precisely saucer-shaped, with a degree of geometric regularity that seemed to have no business appearing on a natural body made of ice and dust. And yet, it is a natural body. No intelligence designed it. No technology shaped it. Atlas has been orbiting Saturn since long before human beings existed. Perhaps since before complex life appeared on Earth. It is made of the same materials as Saturn's rings, water ice and trace amounts of reddish organic contamination, loosely packed under gravity so weak it can barely hold itself together. Understanding how nature alone produced an object this geometrically precise requires a journey into the physics of small worlds, the mechanics of ring systems, and a set of conditions so specific that they exist almost nowhere else in the solar system. That journey starts with what Atlas actually is. Atlas is small. That word gets used carelessly in astronomy, where everything is relative and even a modest moon can span thousands of kilometers. But Atlas is small in a way that genuinely challenges the imagination. Its longest dimension, the full span across its widest equatorial axis, measures roughly 41 kilometers. Its shortest dimension, the distance from one pole to the other measured straight through its center, is only about 19 kilometers. If you set Atlas down on a map of a major city, it would not cover the metropolitan area. Its widest span, from one edge of the equatorial disk to the other, is shorter than the length of a marathon course. And its shape makes those numbers stranger. Atlas is not 41 kilometers of roughly spherical rock. It is 41 kilometers of flat disk, wider than it is tall by a factor of more than 2 to 1. Its three principal axes, as measured from Cassini data, are approximately 40.8 kilometers by 35.4 kilometers by 18.6 kilometers. The first two numbers describe its width and breadth across the equatorial plane. The third describes its compressed polar height. That ratio is extreme. Atlas is proportioned less like a world and more like a piece of sporting equipment. Its mass is approximately 5.5 quadrillion kilograms. Written out, that figure is 5.49 times 10 to the 15th power kilograms. In everyday terms, that is comparable to the total mass of all the water in one of Earth's Great Lakes. It is a trivial amount of mass by the standards of planetary science. Earth's moon is roughly 13 million times heavier. Even the smallest major moons of Saturn, like Mimas at about 400 kilometers in diameter, outweigh Atlas by a factor of nearly 7,000. Atlas is not just a small moon. It is one of the tiniest objects in the solar system that any spacecraft has ever examined up close. Then there is the density, and this number is perhaps the most revealing detail of all. Atlas has a mean density of approximately 0.4 grams per cubic centimeter. To grasp what that means, consider some reference points. Liquid water has a density of 1 gram per cubic centimeter. Solid water ice, the kind that floats in your glass, has a density of about 0.9 grams per cubic centimeter. Cork has a density of roughly 0.2. Atlas sits between ice and cork at less than half the density of frozen water. If you could find an ocean large enough to hold it, Atlas would float high above the waterline, bobbing like a piece of packing foam. That density is not consistent with a solid body. It is not consistent with a compacted ball of ice. It tells scientists that Atlas is mostly empty space. It is a loosely packed aggregate of icy particles and dust grains, held together not by chemical bonds or material strength, but by gravity alone. And that gravity is almost unimaginably weak. The surface gravity on Atlas varies depending on where you stand, because the shape is so irregular, but the highest value measured is roughly 0.0017 meters per second squared. Earth's surface gravity is 9.8 meters per second squared. That means the gravitational pull on Atlas is roughly 5,000 times weaker than what you feel standing on the ground right now. 5,000 times. The concept almost stops making sense at that scale. Here is what that weakness means in practice. If you stood on the equatorial ridge of Atlas and pushed off the ground with the same effort you would use to step over a curb, you would rise gently into the black sky above and never return. Atlas's escape velocity at its equatorial rim is only about 6 meters per second. That is roughly the speed of a fast run. A casual throw of a baseball would send the ball sailing over the horizon and into orbit around Saturn. A running jump would launch you permanently off the surface, drifting away into the ring plane with no way to return unless you carried a thruster. There is no atmosphere to slow you, no air resistance, no wind, no sound. The surface temperature hovers around 81 kelvins, which is roughly minus 192 degrees Celsius, cold enough that water ice behaves almost like rock. Standing on Atlas and looking upward, you would see Saturn dominating an enormous arc of the sky, its banded cloud tops glowing in reflected sunlight. The rings would appear as a razor-thin, luminous line stretching from one horizon to the other, because from Atlas's vantage point, you would be looking at them almost perfectly edge-on. The sun would be a small, intensely bright point of light, roughly 10 times farther away than it appears from Earth, casting long, faint shadows across a surface made of fine-grained frost. You would weigh essentially nothing. The ground beneath your feet would be fragile, powdery, loosely consolidated ice, and the world you were standing on would be, from every visual perspective, the most alien-looking moon in the solar system. To understand how scientists obtained images this detailed of an object this small and this remote, you need to understand what the Cassini spacecraft was doing in April of 2017. It was dying. Cassini had arrived at Saturn on June 30th, 2004, after a nearly 7-year journey from Earth. Over the 13 years that followed, it completed nearly 300 orbits of the planet, discovering new moons, mapping Titan's methane lakes through the haze with radar, flying through the water ice geysers of Enceladus, and producing the most comprehensive survey of a planetary ring system ever conducted. By early 2017, its fuel was running low. Mission controllers at the Jet Propulsion Laboratory faced a decision. They could let the spacecraft drift until its thrusters failed entirely, at which point it would become uncontrollable and might eventually crash into Titan or Enceladus, 2 moons considered potential habitats for microbial life. Contaminating those worlds with earthly microbes carried on the spacecraft's hull was unacceptable. The alternative was to end the mission deliberately, in a way that would squeeze the maximum amount of science from the spacecraft's final months while ensuring it could never collide with a potentially habitable moon. The solution was the grand finale. Beginning in late 2016, Cassini was steered into a series of progressively daring orbits. The first set, called the ring-grazing orbits, sent the spacecraft skimming just past the outer edge of Saturn's main rings, closer than it had ever flown before. These passes brought Cassini within striking distance of the small ring moons that had been too tiny and too close to the rings to target during earlier phases of the mission. The flybys of Pan, Daphnis, Atlas, Pandora, and Epimetheus were all conducted during this ring-grazing phase, each one a carefully choreographed dive that lasted only hours and could not be repeated. After the ring-grazing orbits came the even more daring proximal orbits, during which Cassini threaded the gap between Saturn's cloud tops and the inner edge of the D-ring. A space no spacecraft had ever entered. And finally, on September 15th, 2017, Cassini fired its thrusters one last time to aim itself at Saturn's atmosphere and plunged in, transmitting data until the signal cut out. The Atlas images from April 12th were products of this end-of-life campaign. They exist because engineers chose to spend the spacecraft's remaining fuel on a set of maneuvers that would have been considered too risky earlier in the mission. If Cassini had suffered a thruster failure during any of the ring-grazing passes, the mission would have ended prematurely and without the controlled atmospheric entry that ensured planetary protection. The scientists and engineers accepted that risk because the scientific return was irreplaceable. No other spacecraft had ever been positioned to image Saturn's ring moons at this resolution, and no future mission is designed to study them at comparable range. The Cassini close-ups of Atlas are, as of now, the best images of this moon that may exist for decades. They were purchased with the final months of a spacecraft's life, and they revealed a shape that no one was fully prepared to see at that level of detail. Atlas was discovered in 1980, but not in real time. The discovery came months after the data had been collected, when Richard Terrile, a scientist at the Jet Propulsion Laboratory, was methodically examining photographs taken by the Voyager 1 spacecraft during its flyby of Saturn in November of that year. Terrile identified a faint point of light moving against the background of the rings, tracing an orbit just outside the outer edge of the A-ring. The dot was so small and so faint that it had not been flagged during the initial review of the Voyager images. It was found through careful, patient reanalysis, the kind of work that produces discoveries not through dramatic moments, but through long hours of comparing frames. The moon received the provisional designation S1980S28. It was later confirmed as a genuine satellite and given the formal number Saturn 15, the 15th confirmed moon of the planet. The name Atlas was chosen from Greek mythology, after the Titan condemned to bear the weight of the heavens on his shoulders. The name was selected in part because of the moon's location at the outer boundary of the A-ring, which suggested it might play a role in confining the ring edge gravitationally, holding the ring structure in place the way a bookend holds a row of volumes upright. In the Voyager images, Atlas was nothing more than that dot, a pinpoint of reflected sunlight smeared slightly by the spacecraft's motion. No shape information, no surface detail, no hint of the strangeness that lay beneath the unresolved flicker of brightness. For the next 2 decades, Atlas existed in the scientific literature as an orbital entry and a rough size estimate, a moon known to exist, but understood only in the barest statistical terms. Voyager 2 flew past Saturn in August of 1981, less than a year after Voyager 1. It confirmed Atlas's existence and refined its orbital parameters, but did not pass close enough to reveal any structural detail. The moon remained a dot. Through the 1980s and 90s, ground-based telescopes and the Hubble Space Telescope occasionally observed Saturn's ring region, but Atlas was too small and too close to the overwhelming brightness of the rings to be resolved from Earth's distance. Everything scientists knew about it fit on a single index card. Orbital radius, orbital period, estimated diameter, approximate brightness. Nothing about shape, nothing about density, nothing about what it actually looked like. That changed when Cassini arrived. Within its first 2 years in orbit, the spacecraft's imaging science subsystem captured views of Atlas from distances of tens of thousands of kilometers. Still far too distant for high-resolution surface mapping, but close enough to resolve the overall shape. And immediately something was wrong. The silhouette was not round. It was not elongated in the way most small, irregular moons appear. It was flattened, wider than it was tall, with a bulge at the equator that made the profile distinctly disc-like. Early analyses were cautious. The resolution was limited. But as Cassini accumulated more observations across different viewing geometries and lighting conditions, the flattened shape became unmistakable. By 2005, the equatorial ridge was clearly resolved. Scientists could see that it was not a gentle rounding, but a sharp, distinct band of material protruding from the moon's midsection. The conversation shifted from what is Atlas to what happened to Atlas. 2 landmark papers published in 2007, both in the journal Science, offered the first rigorous answers. Despite its mythological name, Atlas does not hold up anything. The outer edge of the A-ring is maintained primarily by a gravitational resonance with the larger moon Janus, not by Atlas's tiny mass. But the moon's proximity to the ring edge turned out to be central to its story for an entirely different reason. One that had nothing to do with confinement and everything to do with construction. The first evidence that Atlas might be physically unusual came with the Cassini mission. Cassini entered orbit around Saturn on July 1st, 2004, beginning a mission that would ultimately span more than 13 years and transform our understanding of the entire Saturn system. Among its many targets were the small inner moons orbiting near and within the rings, objects too tiny and too close to Saturn to have been studied in detail by any previous mission. Early Cassini images of Atlas, taken from distances of tens of thousands of kilometers, immediately showed that its profile was wrong. It was not roughly spherical like a large moon. It was not elongated like a typical small irregular satellite. It was flattened, compressed, wider than it was tall by an obvious margin. And there was something protruding from its midsection, a band of material that made the silhouette look distinctly disc-like, even at low resolution. As the mission progressed and Cassini made repeated passes through the inner Saturn system, the images grew sharper. By 2005, the equatorial ridge was unmistakable. By 2007, a team led by Carolyn Porco at the Space Science Institute, along with collaborators including Peter Thomas and Derek Richardson, published a landmark analysis in the journal Science. They combined shape measurements from Cassini imagery with gravitational data and numerical simulations to build a detailed picture of how Saturn's small inner moons had formed. Their conclusion was that moons like Atlas and Pan had grown by accreting ring material around denser interior cores, with the resulting bodies achieving the maximum sizes physically possible given the gravitational environment near Saturn's rings. The equatorial ridges, they proposed, were the last features to form, built up from ring particles that settled onto the moon's equatorial planes after the surrounding ring material had flattened into its present ultra-thin disk. The same year, a second paper by Sébastien Charnoz and colleagues, also published in Science, went further. They modeled the ridges specifically as what they called terminal accretionary ornaments, kilometers thick piles of ring particles that had accumulated on the equatorial surfaces of already formed moon cores. The ridges were not geological features in the traditional sense. They were not mountains pushed up by internal forces or valleys carved by erosion. They were deposits, layers of icy material that had drifted in from the surrounding ring environment and settled, slowly and steadily, on the one part of the moon's surface where the geometry of the ring plane allowed them to arrive. That idea was elegant. It was physically grounded, and it pointed to something deeply strange about what Atlas actually represents. To truly understand that strangeness, you need to understand the world Atlas lives inside. Saturn's main ring system is one of the most visually spectacular structures in the known universe, but its physical reality is far more extreme than its beauty suggests. The rings are composed overwhelmingly of water ice particles, ranging in size from grains smaller than a pinch of sand to irregular chunks several meters across. The total mass of the entire main ring system is estimated to be roughly equivalent to the mass of Mimas, Saturn's smallest major moon, a body about 400 kilometers in diameter. That mass is spread across a disk spanning more than 280,000 kilometers in diameter. And that disk, despite its staggering width, is almost incomprehensibly thin. In most regions, the ring thickness is only about 10 meters. Some areas may be even thinner. Imagine a sheet of paper scaled up to the width of the distance between the Earth and the Moon. That is roughly the proportional thickness of Saturn's rings. They are the flattest large-scale natural structure known to science, and the physics of why they are so flat is directly connected to why Atlas looks the way it does. Every particle in the rings orbits Saturn independently, following the same gravitational laws that govern planets. Particles closer to Saturn orbit faster. Particles farther out orbit slower. When particles at slightly different orbital distances drift close to one another, the difference in their speeds creates gentle collisions, nudges rather than crashes. Over millions of orbits, these collisions do two things. They circularize the orbits of the particles, removing any tendency to drift above or below the central plane, and they dissipate kinetic energy, flattening the distribution into a thinner and thinner disk. The rings are thin because collisions enforce thinness. Any particle that strays above or below the plane gets bumped back in. The result is a disk so flat that it nearly vanishes when viewed edge-on from Earth, as it does approximately every 15 years when Saturn's tilt aligns the ring plane with our line of sight. Atlas orbits just outside the outer edge of the A-ring, in a sparse region called the Roche division that separates the main rings from the narrow, twisted F-ring farther out. It traces its path roughly 900 kilometers beyond the A-ring's outer boundary. That places it in a transitional zone, a border region where the dense particle environment of the main rings gives way to the relative emptiness beyond. It is close enough to the ring edge that material from the A-ring can, under the right conditions, drift outward into its gravitational influence. And its own gravity, weak as it is strong enough to capture particles that approach gently, at low relative velocities, in nearly matching orbits. In 2004, Cassini imaging revealed something that deepened the connection between Atlas and its ring environment even further. Atlas has its own faint ring. A thin, temporary arc of material shares its orbit, likely composed of particles knocked from the moon's surface by micrometeorite impacts, or slowly escaping from the equatorial ridge under the near-zero gravity, Atlas does not simply orbit near Saturn's rings. It participates in them. Material flows from the rings toward the moon, accumulates on its surface, and occasionally drifts back outward. Atlas is not a bystander in the ring system, it is a component of it. To grasp why that relationship matters, it helps to understand the ring system itself in slightly more detail. Saturn's main rings are not a single uniform sheet. They are divided into distinct regions, labeled by letter in the order they were discovered, which does not correspond to their order outward from the planet. The D ring sits closest to Saturn, a faint and tenuous band barely visible even to Cassini's cameras. Outside, it lies the C ring, brighter but still relatively transparent. Then comes the B ring, the densest and most opaque section of the entire system. A wall of ice so thick with particles that starlight cannot pass through it. Beyond the B ring is the Cassini division, a broad apparent gap roughly 4,700 kilometers wide that was first observed from Earth in the 17th century. The gap is not truly empty. It contains its own thin ringlets and diffuse material. But compared to the blinding brightness of the B ring on one side and the A ring on the other, it looks dark. The A ring is the outermost of the main bright rings. It is somewhat less dense than the B ring, but still packed with ice particles ranging from grains the size of sand to chunks the size of small houses. Within the A ring sit two well-known gaps. The Encke gap, roughly 325 kilometers wide, is home to the moon Pan. The much narrower Keeler gap, only about 42 kilometers across, contains Daphnis. Both moons actively maintain their gaps through gravitational interaction, sweeping particles from their orbital paths and creating visible wave patterns in the ring material on either side. Beyond the A ring's outer edge lies the Roche division, a relatively sparse transitional zone roughly 3,400 kilometers wide. And it is here, orbiting just 900 kilometers outside the A ring's boundary, that Atlas traces its path. Farther still lies the narrow, braided F ring, a dynamic and chaotically structured band shepherded by the moons Prometheus and Pandora. Beyond the F ring, the rings become increasingly tenuous, stretching outward through the G ring and finally the enormous, diffuse E ring generated by Enceladus's plumes. The particles composing the main rings are overwhelmingly water ice. Spectroscopic measurements by Cassini's instruments confirm this composition across the A, B, and C rings, with minor contamination by silicates, organic compounds, and a reddish chromophore whose exact chemical identity remains debated. The particles are not uniformly distributed. They clump and stream and organize themselves into structures driven by gravitational resonances with Saturn's moons, creating spiral density waves, vertical corrugations, and the straw-like elongated aggregates called self-gravity wakes that give certain ring regions a granular texture when viewed at high resolution. The total mass of this entire system, all the trillions upon trillions of individual particles spread across a disk more than 250,000 kilometers in diameter, is remarkably small. Cassini's final gravity measurements estimated the ring mass at only about 40% of the mass of Mimas, Saturn's smallest major moon. If you gathered every particle in Saturn's rings into a single sphere of solid ice, that sphere would be only about 320 kilometers in diameter, smaller than Mimas itself. The rings are visually overwhelming and physically modest at the same time. An immense structure made of a surprisingly small amount of material, spread extraordinarily thin. This is the environment Atlas inhabits. Not the vast empty space between planets, not the slow, cold drift of the outer solar system. Atlas lives inside one of the most dynamic and visually complex structures in the known universe, orbiting at its outer margin, interacting with its particles, wearing its chemical fingerprints on its surface. The moon is not just near the rings, it is part of the ring ecosystem, a participant in the same physics that governs every particle and gap and wave in the disk surrounding it. This is what sets Atlas apart from almost every other strangely shaped object in the solar system. Asteroids like Bennu and Ryugu have peculiar top-like shapes because of how solar radiation gradually spun them up, redistributing loose surface material toward their equators. Comets like 67P have bilobed shapes because two separate objects collided at low speed and stuck together. These are fascinating objects with fascinating histories, but their explanations are relatively self-contained. The shape comes from within, from the object's own spin or its own collision history. Atlas is different. Its shape does not come only from its own properties, it comes from the system it is embedded in. Saturn's rings are not a backdrop. They are not scenery hanging behind the moon like a painted curtain. They are active participants in shaping it. The ring particles, the tidal forces from Saturn, the razor-thin geometry of the orbital plane, the impossibly weak gravity that cannot resist whatever form is imposed from outside. All of these forces work together to produce a moon that looks less like a world and more like a manufactured object set adrift among the ice. The question forming now is the same one that has driven planetary scientists since those first sharp Cassini images arrived on Earth. If gravity did not pull Atlas into a sphere the way it pulls planets and large moons into spheres, what did shape it? What process could possibly produce something this geometrically clean on a natural body made of ice dust, held together by almost no gravitational force at all? The answer begins with a rule so fundamental to how the universe organizes matter that most people never think to question it. Every planet you have ever seen in a photograph is round. Every star is round. Every major moon, from our own to the 4 great satellites of Jupiter, is round. It seems inevitable. It seems like the natural shape of things in space. It is not inevitable. It is a consequence of a threshold, a specific minimum size below which gravity loses its ability to enforce a spherical shape, and below which a body is free to take on any form that its history has given it. Atlas is vastly smaller than that threshold, and what that means for the kind of shapes it can hold, the kind of forces that can sculpt it, and the reason it ended up looking like something from a different century's fever dream, that is where this story turns next. There is a question that sounds almost too simple to be worth asking. Why are planets round? You have seen the photographs your entire life. Earth, Mars, Jupiter, Saturn. Every large world in every image is a sphere, or very nearly one. It feels like a law of the universe, as though roundness is the default shape of anything floating in space. It is not. Roundness is not a default. It is an achievement. It is what happens when a body accumulates enough mass that its own gravity overwhelms every other force, trying to hold its shape in some other configuration. And below a specific threshold of size and mass, that achievement is never reached. The object remains whatever shape its history gave it, no matter how strange that shape might be. The principle governing this threshold has a name. Scientists call it hydrostatic equilibrium. The term comes from fluid mechanics, where it describes the state of a fluid at rest under its own weight, every internal pressure perfectly balanced against every gravitational force. Applied to a planet or a moon, it means the same thing. A body in hydrostatic equilibrium has been reshaped by its own gravity until every high point has been pulled down and every low point has been pushed up, until the surface settles into the lowest energy configuration available. For a non-rotating body, that configuration is a perfect sphere. For a rotating body, it is a slightly flattened sphere, wider at the equator than from pole to pole, because the spin creates a centrifugal bulge. Either way, the result is smooth, symmetrical, and recognizably round. Here is how it works in physical terms. Every piece of matter inside a large body exerts a gravitational pull on every other piece. In a small body, that pull is negligible. The structural strength of the material, whether it is rock, ice, or iron, easily resists gravity's attempt to rearrange things. A boulder can hold its jagged shape indefinitely, because the molecular bonds inside the stone are vastly stronger than the boulder's own gravitational field. But as you add mass, the gravitational pull grows. It increases with every additional kilogram, and at some point, it becomes strong enough that the rock at the center of the body begins to yield. Not through melting necessarily, though internal heat can help. Through a slower process called plastic deformation, where sustained pressure gradually causes even solid material to creep and flow like a thick liquid over geological timescales. The mountains get pulled inward, the valleys get pushed outward. Slowly, over millions of years, gravity wins. The body relaxes into a sphere. The threshold where this happens depends on what the body is made of. Rock is strong. It resists deformation stubbornly. An object composed primarily of silicate rock needs to be at least 600 to roughly 1,000 kilometers in diameter before its gravity can overcome the material strength and force it toward roundness. Ice is weaker. It deforms under pressure more readily than rock. An icy body can reach hydrostatic equilibrium at a smaller size, roughly 400 to 500 kilometers in diameter. Below those thresholds, gravity simply does not have enough leverage. The body keeps whatever shape it has. Consider a few examples from the solar system to see this boundary in action. Mimas, the innermost of Saturn's major moons, has a diameter of approximately 396 kilometers. It is round, or close to it, a slightly lumpy sphere dominated by the enormous Herschel crater that gives it an accidental resemblance to a fictional space station. Mimas sits right at the lower edge of the rounding threshold for icy bodies. It barely qualifies. If it were much smaller, it would not have achieved its roughly spherical form. Step down in size and the roundness vanishes rapidly. Hyperion, another moon of Saturn, is roughly 270 kilometers in mean diameter. It is a chaotic, sponge-like body riddled with deep craters, tumbling through space with no fixed rotation axis. It looks like a piece of pumice stone pulled from a volcanic vent. There is nothing round about it. Its gravity is too feeble to reshape its battered exterior, so it carries every scar from every impact it has ever received. Phobos, the larger of Mars's two moons, is roughly 22 kilometers across. It is a lumpy, cratered, oblong body shaped like a misshapen potato. Deimos, the smaller one, is only about 12 kilometers across and looks like a smoothed pebble. Neither has anything approaching a spherical profile. Their gravity is a rounding error, in the most literal sense imaginable. Now, place Atlas in this lineup. Atlas is roughly 30 kilometers in mean diameter. It would fit comfortably inside one of the smaller craters on Earth's moon. It is more than 13 times too small to reach the icy body rounding threshold. Gravity does not even begin to compete with the structural integrity of this ice. If you built a miniature atlas out of packed snow and set it in space, the gravitational pull of that snow on itself would be so weak that the pile would hold whatever shape you gave it for the remaining age of the solar system. You could sculpt it into a cube, a pyramid, or a flying saucer, and gravity would never smooth it out. The internal forces that reshape large worlds into spheres are, at Atlas's scale, essentially absent. This is the first critical piece of the puzzle. Atlas looks like a flying saucer, not despite being natural, but because it is so small and so light that nature has no mechanism to correct its shape. A larger body with the same internal structure would long since have been crushed into a sphere by its own weight. Atlas is too tiny to be rounded, too fragile to be compressed, too loosely packed to resist whatever external force shaped it. It is frozen in a form that a more massive world would never be allowed to keep. But this only explains why the saucer shape can persist. It does not explain how it got there in the first place. For that, you need to understand the environment Atlas inhabits. Not just the cold vacuum of space, but a specific gravitational neighborhood that imposes its own extraordinary rules on every object inside it. In 1849, a French astronomer named Edouard Roche published a set of calculations that would fundamentally change how scientists understood the relationship between planets and the moons and ring particles orbiting near them. Roche asked a simple question. How close can a moon approach a planet before the planet's tidal forces tear the moon apart? The answer depended on two things: the densities of the planet and the moon, and the distance between them. For a moon held together only by its own gravity, with no material strength to reinforce its structure, Roche calculated that the critical distance was approximately 2.44 times the planet's radius. Inside that distance, tidal stretching would overpower the moon's self-gravity, pulling it to pieces. Outside that distance, the moon's gravity could hold it together. That critical distance became known as the Roche limit. And in the Saturn system, it defines the most important invisible boundary in the entire neighborhood. Saturn's classical Roche limit, in the idealized equal density case, sits at roughly 147,000 kilometers from the planet's center. But the limit shifts depending on the density of the orbiting body. For a body as porous and lightweight as Atlas, with a density of only 0.4 grams per cubic centimeter, the relevant Roche limit extends much farther out, to approximately 177,000 kilometers. Atlas orbits at approximately 137,700 kilometers. It sits roughly 39,000 kilometers inside its own Roche limit, deep within the zone where Saturn's tides overpower its self-gravity. And yet, Atlas exists. It has not been torn apart. It circles Saturn every 14 hours, intact, orbit after orbit, year after year. The reason is that Roche's original calculation assumed a body held together only by gravity. At Atlas's tiny size, gravity is not the primary force holding it together. Material cohesion is. The molecular bonds within and between the icy particles composing Atlas. The simple, physical stickiness of ice grains frozen together in vacuum are far stronger than Atlas's own gravitational self-attraction. The Roche limit is a meaningful boundary for large bodies, hundreds of kilometers across, where gravity is the dominant structural force. For a body the size of Atlas, material cohesion takes over. The moon holds together the way a snowball holds together. Not because gravity compresses it into shape, but because the grains are stuck to one another. But survival is not the same as comfort. Atlas holds together, yes, but it does so in a gravitational environment that is actively hostile to the idea of a solid body existing at all. The Roche limit is not a wall. It is not a line you cross once and forget about. It is a gradient, a steadily increasing tidal stress that grows stronger with every kilometer closer to Saturn. Atlas sits inside that gradient, and the consequences are constant. Consider what tidal forces actually do at Atlas's orbital distance. Saturn's gravitational pull on the side of Atlas that faces the planet is measurably stronger than its pull on the side facing away. This difference, this tidal gradient, tries to stretch Atlas along the Saturn-facing axis, pulling the near side toward the planet and the far side away from it. On a large moon with substantial self-gravity, this stretching is negligible compared to the body's own gravitational compression. On Atlas, the contest is almost even. The tidal stretching force and Atlas's self-gravity are the same order of magnitude. The moon is not being torn apart, but it is being tugged at the seams continuously, held intact by cohesion working against a tidal field that would happily pull it to pieces if the molecular bonds let go. This has a practical consequence that is easy to state but difficult to fully absorb. The surface of Atlas does not hold onto loose material the way most worlds do. On Earth, if you pick up a stone and drop it, gravity pulls it back down. On our moon, the same thing happens, just more slowly. On Atlas, particularly near the equatorial ridge where the surface is closest to the edge of the moon's own gravitational domain, the situation is far less certain. A particle resting on the equatorial rim of Atlas sits near the boundary between the moon's gravity and Saturn's tidal pull. If that particle were dislodged by a micrometeorite impact, given even a small nudge outward, it might not return. It could drift off the surface, enter a nearby orbit, and join the sparse population of ring particles circling Saturn in Atlas's orbital neighborhood. The moon does not so much hold its surface material as balance it, keeping it in place by the narrowest of gravitational margins. This marginal grip explains something important about why accretion at Atlas's location is such a delicate process. Farther from Saturn, beyond the Roche limit, gravity wins decisively. Particles that drift close to a moon are captured easily and accumulate quickly. Deep inside the Roche limit, closer to Saturn, tidal forces win decisively. Particles cannot clump at all, which is why the ring material remains as countless individual fragments, rather than assembling into larger bodies. Atlas occupies the border between these two regimes. Accretion is possible here, but only barely. Particles can be captured, but only if they approach gently enough and slowly enough that the moon's feeble gravity can claim them before Saturn's tides pull them away. The ridge on Atlas was not built by a process operating with wide tolerances and comfortable margins. It was built at the edge of what is gravitationally permitted, in a zone where the difference between capture and escape is measured in centimeters per second. This distinction has profound consequences for what shapes are possible. A large moon near a planet, held together by gravity, must assume a shape that balances gravitational compression against tidal stretching. Those shapes are well studied. They are called Roche ellipsoids, Smooth, elongated ovals stretched along the line connecting the moon to the planet. A body in this regime cannot have sharp edges, ridges, or irregular protrusions. Gravity smooths everything. Atlas is not in this regime. Its self-gravity is too weak to enforce any particular shape at all. But Saturn's tidal forces still act on it. Those forces stretch Atlas slightly along the Saturn-facing axis, the direction that connects the moon to the planet. This is the same kind of tidal distortion that raises ocean tides on Earth, except at Atlas's distance and with Atlas's negligible mass, the effect is subtle. It elongates the body gently in one direction, but does not create a disk. It does not create a ridge. Tidal stretching acts along a single axis. The equatorial ridge of Atlas wraps around an entire circumference. These are geometrically incompatible. Tidal forces shape the body's overall elongation, but cannot explain the ridge. There is another force acting on Atlas that matters: centrifugal force from its own rotation. Atlas is tidally locked to Saturn, meaning it rotates exactly once for every orbit, always presenting the same face toward the planet. Just as Earth's moon always shows the same face to Earth. Its rotation period matches its orbital period exactly. That spin generates a very slight centrifugal bulge at the equator, the same effect that makes Earth a few dozen kilometers wider at the equator than from pole to pole. But Atlas is not spinning fast enough for centrifugal force to create a dramatic equatorial feature. If you compare Atlas's rotation rate to its size, the centrifugal contribution to its shape is minuscule. Some fast-spinning asteroids develop equatorial bulges from centrifugal effects, a phenomenon studied extensively in near-Earth objects where solar radiation gradually increases the spin rate over millions of years. Atlas does not rotate fast enough for this mechanism to apply. Its 14-hour rotation is locked, stable, and slow relative to what will be needed to fling material outward along the equator. So you arrive at a peculiar dead end, or what appears to be one. Gravity cannot round Atlas, tidal forces cannot create the ridge, centrifugal force cannot create the ridge. None of the internal forces that shape most objects in the solar system can explain how Atlas ended up looking like a manufactured disk with a sharp equatorial belt. The dead end is an illusion. It only exists if you think of Atlas as a body shaped exclusively by forces acting from within. The moment you look outward at the ring system surrounding it, the dead end dissolves. Because the shaping force does not come from inside the moon. It comes from outside. It comes from the vast, flat, icy disk in which Atlas is embedded. Before reaching that explanation, though, it is worth pausing to appreciate how thoroughly Atlas defies the normal categories scientists use to organize small bodies. In planetary science, small objects are generally understood through a few well-studied templates. There are rubble pile asteroids, loosely bound gravitational aggregates of rocky fragments held together by weak self-gravity and van der Waals forces. Objects like the near-Earth asteroid Itokawa, visited by Japan's Hayabusa spacecraft, fall into this category. They are lumpy, peanut-shaped, and clearly assembled from smaller pieces. Their shapes make intuitive sense. They look like piles of debris because that is what they are. There are contact binary bodies, objects formed when two smaller bodies collided at very low speed and stuck together without shattering. The Kuiper Belt object, Arakoth, visited by New Horizons in 2019, is the most famous example. A snowman-shaped body composed of two distinct lobes joined at a narrow neck. Again, The shape is strange, but understandable. You can look at it and see the collision that made it. There are icy moons with surfaces sculpted by internal geological processes. Enceladus, 500 kilometers across, has a south polar region cracked open by tidal heating, venting plumes of water vapor and ice grains into space. Its shape is spherical because it is large enough for gravity to enforce roundness, and its surface features are products of internal energy. Iapetus, 1,470 kilometers in diameter, has its own equatorial ridge, but at a vastly larger scale and with a very different proposed origin, possibly connected to an ancient period of faster rotation or the collapse of a now vanished ring of its own. Then there are the chaotic tumblers, like Hyperion, small enough to avoid roundness and battered enough to look like cosmic wreckage. Atlas does not fit any of these templates. It is not a rubble pile, because its equatorial ridge is smooth, organized, and geometrically precise in a way that random gravitational accumulation does not produce. It is not a contact binary, because it does not have two lobes joined at a neck. It is not shaped by internal geology, because it has no internal energy source, no tidal heating, no geological activity. And it is not a battered, cratered wreck, because its equatorial ridge shows surprisingly few impact craters compared to its polar regions, suggesting the ridge material is younger or was deposited more recently than the core body. Atlas is something else. It is a body that was sculpted from the outside by a process that deposits material preferentially along one geometric plane, building a structure that the moon's own gravity is too weak to erase. That process is connected to the single most defining feature of Atlas's environment, the flatness of Saturn's rings. The rings are not just flat, they are almost impossibly flat, maintained in their knife-edge thinness by the same collisional physics that circularizes particle orbits. Any material that enters the ring plane tends to stay in the ring plane. Any material that strays above or below it gets bumped back, and any moon orbiting in or near the ring plane receives material from a specific direction, the equatorial plane, and only the equatorial plane. Picture what this means for a small body with negligible gravity orbiting at the edge of a flat disk of icy particles. The particles approach from the disk plane, which aligns with the moon's equator. They arrive at low relative velocities, drifting gently into the moon's gravitational reach. When they land on the equator, because that is where the ring plane intersects the moon's surface. They do not pile up at the poles, because no ring material approaches from above or below. The delivery system is directional. It feeds the equator, and only the equator, orbit after orbit, century after century. Over long stretches of time, this directional delivery builds a ridge. Layer by layer, grain by grain, icy material accumulates along the equatorial belt of the moon. The ridge grows outward, extending the moon's profile in the equatorial plane while the polar regions remain untouched. The result is a disk, a saucer, a shape that looks artificial precisely because it is the product of a process so geometrically constrained that it could only produce one outcome. That process, the accretion of ring material onto a moon's equator, is the leading explanation for why Atlas looks the way it does. It is a mechanism that exists nowhere in the solar system outside the ring environments of the giant planets. And the specific details of how it works, what it requires, what it predicts, and how it was confirmed by Cassini's final and most daring observations are what we turn to next. There is a reason the equatorial ridge on Atlas looks so clean. There is a reason its surface texture differs between the ridge and the poles. There's a reason Atlas's density is so absurdly low. And there is a reason Pan, another moon orbiting inside Saturn's rings in a gap of its own, has an almost identical saucer profile despite being a separate body in a separate location. All of these details point to the same mechanism. And the evidence for that mechanism was gathered during a sequence of flybys so close that the spacecraft passed through streams of ring particles to reach its targets. The machinery that built the flying saucer is Saturn's ring system itself. What comes next is how that machinery works. When you look at Atlas from a distance, the equatorial ridge appears as a single clean line, a geometric accent on an already strange body. Cassini's closest images tell a different story. Up close, the ridge is not a knife edge. It is a broad, gently sloping apron of material that extends roughly 20 to 30 degrees of latitude on either side of the equator, blending into the main body above and below, but maintaining a distinctly smoother surface texture than the polar terrain surrounding it. The transition between the ridge material and the older core body is visible, not as a sharp boundary, but as a change in roughness, a shift from the pocked and cratered surface of the poles to the softer, less battered surface of the equatorial band. That textural difference is one of the most important clues scientists have about how the ridge was built. The polar regions of Atlas, the areas above and below the equatorial bulge, are rougher. They carry more visible impact craters, more irregular terrain, more of the scarred and pitted texture you would expect on a surface that has been exposed to micrometeorite bombardment for a very long time. The equatorial ridge, by contrast, is smoother. Its surface has fewer large craters. It looks younger. Not young in the sense of geological activity or recent eruptions. Atlas has no internal heat to drive anything like that, but young in the sense that its surface appears to have been resurfaced or deposited more recently than the core body underneath. This difference matters enormously. If Atlas were a single monolithic object, shaped in one event and left unchanged afterward, you would expect uniform cratering across its entire surface. Older surfaces accumulate more craters. Younger surfaces have fewer. The fact that the equatorial ridge is less cratered than the poles tells scientists that the ridge formed after the core body had already been exposed to space for a significant period. The ridge was added later. It is a secondary feature, layered onto a pre-existing moon like icing spread around the middle of a cake that was already baked. That observation was central to the model proposed in 2007 by Carolyn Porco, Peter Thomas, Joseph Weiss, and Derek Richardson, published in the journal Science. Their work drew on Cassini shape measurements, density estimates, and numerical simulations of gravitational accretion near Saturn's rings to construct a coherent history of how Saturn's smallest inner moons formed. The picture they arrived at was elegant and specific. It was a two-stage process. Stage 1 involved the formation of the core body. In the early history of Saturn's ring system, the rings were likely thicker and more massive than they are today. Within that thicker disk, gravitational clumping and low-speed collisions could produce small solid bodies, essentially seeds, ranging from perhaps a few kilometers to roughly half the present diameter of the moons we see now. These core bodies would have had shapes approximating what physicists call a Hill sphere, the teardrop-shaped region around a small body where its own gravity dominates over the tidal pull of Saturn. A body growing inside a thick ring would accrete material from all directions, above and below the ring plane as well as from within it, producing a shape that was roughly ellipsoidal rather than flat. That core would have been denser than the loose ring material around it, composed of more compacted ice, or possibly incorporating silicate fragments from the originals event that created the rings. Stage 2 began after the rings thinned. Over time, the same collisional dynamics that flatten any orbiting disk of particles compress Saturn's rings into their present configuration. A sheet so thin that its vertical extent is measured in single-digit meters across most of its span. Once the rings reached this extreme thinness, the geometry of accretion changed fundamentally. Material could no longer approach a moon from above or below. It could only arrive from within the ring plane, which aligns precisely with the moon's equatorial plane because the moon's orbit lies in the same flat disk. Any ring particles drifting close enough to the moon to be captured gravitationally would land on the equator and stay there, accumulating in a belt that thickened with each passing orbit. Porco and her team estimated that the core of Atlas constitutes roughly 1/3 to 1/2 of the moon's present total volume. The remainder, including the entire equatorial ridge, is accreted ring material. The mantle density they modeled was approximately 0.15 grams per cubic centimeter, astonishingly low, consistent with an extremely fluffy, porous pile of ice grains, barely held in place by Atlas's feeble gravitational field. The core density they estimated was higher, around 0.9 grams per cubic centimeter, closer to solid water ice. This two-component structure, a denser core buried inside a much less dense envelope of accreted material, neatly explains Atlas's overall bulk density of approximately 0.4 grams per cubic centimeter. It is an average of two very different materials in two very different states of compaction. The same year, in the same issue of Science, a complementary paper by Sebastian Charnow, André Braic, Peter Thomas, and Carolyn Porco focused specifically on the equatorial ridges of Atlas and Pan. Their analysis went deeper into the mechanics of how ring particles could be delivered to the equatorial surface of a moon embedded in or adjacent to the ring system. The critical insight involved the Lagrange points, the gravitational gateways that exist in any system where a small body orbits a much larger one. Every moon orbiting Saturn has a set of 5 Lagrange points, locations where the gravitational pull of Saturn, the gravitational pull of the moon, and the centrifugal force of the orbital motion all balance in specific ways. 2 of these points, designated L1 and L2, sit along the line connecting the moon to Saturn, one on the Saturn-facing side and one on the opposite side. They mark the edges of the moon's gravitational domain, the boundaries beyond which Saturn's gravity dominates. Ring particles drifting near these boundaries can be funneled through the L1 and L2 gateways and drawn onto the moon's surface. Because these gateways lie in the equatorial plane, the material they deliver arrives at the equator. The particles do not have the velocity or the trajectory to reach the poles. They land where the ring plane meets the moon, and nowhere else. To appreciate how strange this process is, follow a single particle through its journey from ring to ridge. Imagine an ice grain roughly 1 centimeter across, one of the countless fragments orbiting Saturn in the outermost reaches of the A-ring. It has been circling the planet for perhaps millions of years, colliding occasionally with its neighbors, slowly migrating outward through random exchanges of angular momentum, drifting toward the ring's outer boundary, one infinitesimal adjustment at a time. Eventually, this particle reaches the region of space where Atlas's gravitational influence begins to matter. The boundary of that region, the Hill sphere, extends only about 20 kilometers from Atlas's center in the radial direction, compressed into a teardrop shape by Saturn's overwhelming tidal field. The particle does not plunge inward. It drifts. The velocity difference between the particle's natural orbit and Atlas's orbit is measured not in kilometers per second, but in centimeters per second. In the frame of reference of the Moon, the particle is barely moving. It floats in following a gentle arc shaped by the combined gravity of Saturn and Atlas, curving through one of the Lagrange point gateways and descending toward the Moon's surface at the pace of a slow walk. When it arrives, the impact is not an impact in any dramatic sense. At centimeters per second, the collision carries less energy than a soap bubble popping against your skin. The particle touches the surface, bounces perhaps once or twice in the negligible gravity, and settles into a shallow depression among thousands of other grains that arrive the same way. There is no flash, no crater, no debris cloud, just a quiet addition of one more grain to a ridge that has been accumulating them for longer than human civilization has existed. This gentleness is fundamental to why the ridge looks the way it does. High-speed impacts shatter material. They excavate craters, melt ice, and scatter debris across the surface. The ring accretion process does none of these things. The arriving particles are so slow that they do not damage the surface they land on. They do not bury themselves. They simply rest on top of whatever was already there, adding their mass to the growing structure without disrupting it. The result is a surface that is smooth and fine-grained rather than rough and cratered, exactly matching what Cassini observed on Atlas's equatorial ridge. And the process is relentless, not continuous in the sense of a steady stream, but persistent across timescales that dwarf any human frame of reference. Each orbit brings Atlas past the ring edge again. Each passage offers another opportunity for particles near the boundary to drift close enough to be captured. The rate of accretion may be extraordinarily low by terrestrial standards, perhaps only a few kilograms of material per orbit, perhaps less. But multiplied across millions of years and hundreds of millions of orbits, those tiny additions compound. A few kilograms per orbit across 10 million years of 14-hour orbits produces a mass measured in trillions of kilograms. The ridge did not form in a catastrophe. It formed in patience, one grain at a time, with a consistency that only orbital mechanics can provide. There's a specific elegance to this picture that the raw numbers do not fully convey. The ridge exists because three things happened to converge at one location. The ring provided the raw material. The thin disk geometry restricted the delivery angle, and Atlas's own weakness, its inability to gravitationally reshape whatever it received, preserved the result. A stronger body would have absorbed the material into a thicker, rounder shell. A body in a different orbit would never have received it. A body near a thicker ring would have been buried uniformly rather than belted at the equator. Everything about the ridge is a consequence of this moon being exactly as small, exactly as weak, and exactly as close to exactly this kind of ring as it is. Charnow and his colleagues described the equatorial ridges as terminal accretionary ornaments. That phrase is precise and revealing. Terminal because the ridges represent the final stage of accretion, the last material to be added after the ring environment had already reached its current thin disk configuration. Accretionary because the ridges grew by accumulation, particle by particle, over time rather than through a single dramatic event. And ornaments because the ridges sit on top of a pre-existing body like decorative additions, physically distinct from the core they surround. Their model predicted several features that Cassini observations later confirmed. First, the ridge material should be smoother and less cratered than the core surface, because it was deposited later. Confirmed. Second, the ridge should be composed of lower density material than the core, because it is loosely packed ring debris rather than compacted ice, confirmed by the overall density measurement, which requires a dense core surrounded by something very fluffy. Third, the ridge should show slight asymmetries connected to the moon's orbital eccentricity, because a moon on a slightly elliptical orbit sweeps through different densities of ring material at different points in its path. Atlas has a measurable orbital eccentricity, and its ridge does show asymmetries. The ridge is not perfectly uniform. It is slightly more rounded in some quadrants, and slightly more angular in others, with subtle depressions that correspond to variations in the rate of material delivery. In 2021, a team led by Alice Quillen extended this accretion model further. Working from the Charnot framework, Quillen and her colleagues examined the torque that accreted material would apply to the moon as it accumulated. A key constraint emerged. For the ridge to grow without disrupting the moon's tidal lock with Saturn, the rate of accretion had to remain below a certain threshold. If material piled on too quickly, the added mass would shift the moon's center of gravity and potentially break the synchronous rotation, flipping or tumbling the body rather than allowing orderly ridge growth. This placed a minimum duration on the ridge building process. The ridge could not have formed overnight. It required a sustained, gentle feeding from the ring environment over a long period, consistent with the gradual depletion of ring material near Atlas's orbit. Quillen's team also explored how the shape of the ridge depends on the geometry of accretion. If ring particles arrive from a symmetric gap, with equal amounts of material available on both the Saturn-facing and anti-Saturn sides, the ridge grows evenly around the equator. If the gap is asymmetric, with more material available on one side, the ridge develops lobes and thickness variations. The depressions visible in Atlas's ridge could be explained by accretion from an asymmetric gap, a prediction consistent with the slight orbital eccentricity that causes Atlas to oscillate gently back and forth relative to the ring edge during each orbit. But the ring accretion model is not the only explanation on the table. In 2018, a team led by Adrien Leloup, Martin Utzi, and Martin Rubin at the University of Bern proposed an entirely different mechanism for producing the saucer shapes of Saturn's inner moons. Their work, published in Nature Astronomy, used smoothed particle hydrodynamic simulations, a computational technique that models material as a collection of interacting particles rather than as a continuous medium, to study what happens when two similar-sized moonlets collide at low velocity within Saturn's Roche zone. The results were striking. When two moonlets of roughly equal mass collided nearly head-on at speeds between 1 and 5 times their mutual escape velocity, the simulation produced flattened objects with pronounced equatorial ridges. The ridge in these simulations was not accreted material from the rings. It was material squeezed outward from the interior during the merger itself, like dough pressed between two hands, flattening and spreading at the contact plane. The white, highly strained material in the simulations, representing surface layers deformed and redistributed during impact, concentrated at the equator, while the less affected original material remained at the poles. The shapes produced by these near head-on mergers closely resembled Atlas and Pan. At slightly more oblique impact angles, the same simulations produced elongated bodies rather than flat disks. These elongated shapes closely match the form of Prometheus, another of Saturn's inner moons, which has a stretched, irregular profile very different from Atlas's saucer. The Leilu team argued that the full spectrum of shapes among Saturn's small inner moons, from the disc-like profiles of Atlas and Pan to the elongated form of Prometheus, could be explained as outcomes of merging collisions at varying impact angles, all taking place at the low velocities expected within Saturn's Roche zone, where orbital speeds are closely matched. This was a powerful result. It offered a single, unified mechanism to explain the shapes of multiple moons, rather than requiring a separate story for each one. But the merging model has a significant limitation when applied to Atlas specifically. The surface texture difference between Atlas's ridge and its poles is difficult to explain through a single collision event. If the ridge were formed by material squeezed out during a merger, the entire surface of the moon would have been processed in the same event, at roughly the same time. There would be no reason to expect a smooth, less cratered equatorial band and a rougher, more cratered polar region. The cratering difference implies a time gap between the formation of the core and the formation of the ridge. A merger event does not produce that gap. Accretion does. The current scientific consensus, as reflected in the 2024 Space Science Reviews paper by Philip Nicholson and colleagues reviewing the origin of Saturn's ring moons, treats both mechanisms as plausible contributors. Atlas's core may have formed through a slow merger or through initial gravitational clumping in the early, thicker ring. The equatorial ridge was then most likely added afterward through sustained accretion of ring particles from the surrounding disk. The two processes are not mutually exclusive. A collision may have created the seed, and the rings may have decorated it. The strongest evidence supporting the accretion model came during the final phase of the Cassini mission. Between December 2016 and April 2017, during the ring-grazing orbits that preceded Cassini's final plunge into Saturn's atmosphere, the spacecraft performed close flybys of 5 small inner moons: Pan, Daphnis, Atlas, Pandora, and Epimetheus. The Atlas flyby on April 12, 2017, was the closest encounter any spacecraft had ever made with this moon, returning the sharpest images of it ever captured. The data returned from these flybys, published in 2019 by Bonnie Boo Rati and a large international team in the journal Science, painted a comprehensive picture of the ring moons as a family of objects shaped by 2 competing environmental processes. The first process is contamination by a reddish material that originates within Saturn's main ring system. The chemical identity of this red material is not fully determined, but it is thought to involve organic compounds, possibly iron-bearing minerals, or a combination of both. This reddish tint is most prominent on the surfaces closest to the rings, giving the moons a faintly warm hue that distinguishes them from the brighter, whiter icy surfaces found farther from the ring plane. The second process is brightening by icy particles and water vapor from Enceladus. Saturn's E-ring, a broad, diffuse ring generated by the water ice plumes erupting from Enceladus's south polar region, extends across much of the inner Saturn system. Particles from this ring gradually coat the surfaces of nearby moons, adding a layer of fresh, bright water ice on top of whatever reddish contamination was already present. The balance between these two processes determines the color and reflectivity of each ring moon's surface. Atlas sits in a region where both processes are active. Its surface carries the reddish tint of ring contamination on the equatorial ridge, where ring material has been most recently deposited, and shows somewhat brighter, cleaner ice on its polar regions, where Enceladus-sourced particles have had longer to accumulate on a surface that is not being continuously refreshed by ring accretion. This color pattern is consistent with the two-component model: an older core surface that has accumulated E-ring frost over time, and a younger ridge surface that is still receiving red-tinted ring material. The density measurements from the close flybys reinforce the accretion interpretation across the entire family of ring moons. Pan, orbiting inside the Encke gap in Saturn's A-ring, has a density of roughly 0.41 grams per cubic centimeter. Daphnis, a much smaller moon inside the narrow Keeler gap, has a density of approximately 0.34 grams per cubic centimeter. Atlas, just outside the A-ring edge, has a density of approximately 0.39 grams per cubic centimeter. All three densities are far below that of solid water ice. All three require porous, loosely packed structures consistent with accreted ring debris surrounding denser cores. The comparison between Atlas and Pan is particularly instructive because it reveals how sensitively the saucer shape responds to local conditions. Pan orbits inside the Encke gap, a wide clearing carved into the A-ring. Pan itself maintains this gap through gravitational interaction, sweeping ring particles from its orbital path. Its overall dimensions are roughly 34 by 31 by 21 kilometers, making it slightly smaller than Atlas, and its density of approximately 0.41 grams per cubic centimeter is nearly identical. But Pan's equatorial ridge is different in character. It is narrower, extending only about 15 to 20 degrees in latitude on either side of the equator, compared to Atlas's 20 to 30 degrees, and it is not smooth. The highest resolution Cassini images, captured during a flyby on March 7th, 2017, roughly 5 weeks before the Atlas encounter, show that Pan's ridge has a pronounced multi-lobed structure, with distinct bumps and thickened sections visible along its circumference. The overall profile has been compared to a ravioli or an empanada, a food-shaped analogy that became briefly famous in the press coverage following the flyby. That lumpier profile is not random. Pan orbits inside a gap, meaning the ring material feeding its ridge arrives from both the inner and outer gap edges simultaneously through different gravitational pathways at slightly different velocities. The material from the inner edge of the gap moves faster than Pan, approaching from the leading side. The material from the outer edge moves slower, approaching from the trailing side. These two streams interact with Pan's tidal field in different ways, depositing their loads at different longitudes along the equator. The result is a ridge with thickness variations that map the asymmetry of Pan's feeding environment. Daphnis offers a different comparison entirely. This moon is much smaller than either Atlas or Pan, only about 9 kilometers across its longest axis. It orbits inside the Keeler Gap, a much narrower slit in the outer A ring, where the tiny moon drifts through a channel only a few times wider than itself, so narrow that Daphnis nearly fills it. Its density is even lower than Atlas's, approximately 0.34 grams per cubic centimeter, making it the most porous of the three and suggesting an even more loosely packed internal structure. The Cassini flyby of Daphnis on January 16th, 2017, revealed a body that is elongated rather than flattened, stretched along one axis like a smoothed stone. Its equatorial features are subtle compared to the dramatic ridges on Atlas and Pan, appearing as narrow raised bands and shallow grooves rather than a thick, protruding belt. This makes sense within the accretion framework. Daphnis is so small that its hill sphere, the region where its gravity dominates over Saturn's, is correspondingly tiny. It captures far less material per orbit than Atlas or Pan, and the Keeler Gap is so narrow that the reservoir of available ring material bordering it is limited. Daphnis receives less material from a smaller supply, and its ridge reflects that scarcity, a whisper where Atlas has a shout. 3 moons in 3 different ring environments. 3 different sizes, 3 different gap geometries, 3 different ridge morphologies. Pan's lumpy ravioli ridge records the dual stream feeding from inside a wide gap. Daphnis's subtle grooves record the scarcity of material bordering a narrow slit. Atlas's broad, smooth belt records the gentle one-sided accretion from an open ring edge with no gap to constrain it. Each moon has been sculpted by its specific location within the ring system, and each carries a shape that would be different if it orbited anywhere else. The mechanism is universal, the details are local, and the results, read correctly, are a map of ring conditions written in the shapes of the moons themselves. 3 moons in 3 different locations within or near Saturn's ring system. 3 different sizes, 3 different orbital environments, 3 different ridge morphologies, and all 3 consistent with the same basic story. A denser seed body forms first. The rings flatten into a thin disk. Ring material then accretes onto the moon's equatorial plane, building features that preserve the geometry of the ring environment in the shape of the moon itself. There is one additional detail from the close flyby data that deserves attention because of what it reveals about the ongoing relationship between the moons and the rings. Cassini's particle detectors measured the charged particle environment around each moon during the flybys. Near Atlas, the instruments detected a tightly confined accumulation of high-energy electrons, a previously unknown microradiation belt occupying the region around the moon's orbit. This feature indicated that Atlas's gravitational influence is actively sculpting its local particle environment, absorbing charged particles at certain energies while allowing others to pass. Atlas is not a passive passenger in the ring system. Even now, even at its tiny mass, it is interacting dynamically with the material surrounding it. The moon and its environment are coupled, exchanging material and energy in a relationship that has been operating since long before any spacecraft arrived to observe it. What emerges from all of this evidence is a portrait of Atlas, not simply as a strange-looking moon, but as an object whose form is a direct physical record of the ring system that shaped it. The saucer profile is not an accident of random collision or an artifact of viewing angle. It is a fossil, a three-dimensional imprint of the conditions that existed in Atlas's orbital neighborhood during the epoch when the ridge was built. The flatness of the ridge records the flatness of the rings. The smoothness of the ridge records the gentleness of the accretion. The asymmetries record the eccentricity of the orbit. And the density records the porosity of ring particles settling under almost no gravitational compression at all. Every detail of Atlas's shape, when read correctly, tells a story about Saturn's rings. The moon is a document written in ice and geometry. And the most extraordinary conclusion that story leads to is not about the moon itself, but about what it means for the relationship between ring systems and the small bodies living inside them. Saturn's rings did not simply surround Atlas, they reached out and physically reshaped it, building features that the moon's own gravity could never have produced and could never erase. The ring system is not just a passive structure orbiting the planet, it is an active sculptor. And Atlas is its most striking work. What that means for how we understand the solar system's capacity to produce objects that look designed without any designer is where this story arrives at its deepest point. There is a moment in the study of any strange object when the strangeness stops being a question and starts being an answer. You spend the early stretch asking how. How did Atlas get its shape? How does the ridge form? How can a natural body look so unnatural? And then, once the mechanics are clear, the question changes. It becomes deeper and quieter. It becomes, what does it mean that this is possible? Atlas is a moon that looks engineered. That statement is not metaphor. It is not exaggeration for the sake of dramatic storytelling. If you showed the Cassini close-up images of Atlas to someone with no context, someone who had never heard of Saturn's rings or equatorial accretion or Roche environments, and asked them what they were looking at, a significant number of those people would describe something manufactured. A disc, a lens, a craft. The symmetry is too clean, the ridge is too precise, the overall profile is too deliberately geometric to register, at first glance, as a product of natural forces operating on ice and dust in the dark. And yet, every force that shaped Atlas is one we understand. Gravity, weak but persistent. Tidal stretching from Saturn, gentle but directional. The flat geometry of a collisionally evolved ring system, delivering material to one plane and one plane only. The inability of a tiny body's self-gravity to erase whatever form is imposed from outside. None of these forces is exotic. None requires unknown physics or speculative mechanisms. They are ordinary processes, the same ones operating throughout the solar system, in every ring system, around every planet with a significant gravitational field. What is extraordinary is not the forces themselves. It is the specific combination of conditions that brought them together at one location, around one small body, in one narrow orbital zone, and the shape that combination produced. That combination does not exist in most places. It requires a planet massive enough to maintain a dense, extensive ring system. It requires that ring system to have flattened into an extremely thin disk so that material delivery is restricted to a single geometric plane. It requires a small moon orbiting at or near the ring edge, close enough to intercept drifting particles, but not so deeply embedded that it clears a wide gap and cuts off its own supply. It requires that moon to be small enough that its gravity cannot reshape the accreted material into a sphere, preserving whatever form the accretion imposes. And it requires enough time for the process to operate, orbit after orbit, building the ridge grain by grain across what may be tens of millions of years or longer. Remove any one of these conditions and the shape disappears. A larger moon in the same orbit would round itself under its own gravity, erasing the ridge as fast as it formed. A moon orbiting farther from the rings would receive no equatorial delivery, and would remain an unremarkable, irregular lump. A thicker ring system would deposit material at all latitudes, building a roughly spherical shell rather than a flat disk. A planet without rings would produce nothing at all. Atlas is the product of a precise intersection of conditions, each one necessary and none sufficient alone. This specificity is part of what makes Atlas so intellectually unsettling. We are accustomed to the idea that nature produces beauty. Crystal lattices, spiral galaxies, the hexagonal storm at Saturn's North Pole. These are all striking, but they are recognizably natural. They have the organic complexity, the slight imperfections, the fractal irregularity that the human eye associates with processes that emerge from physical law rather than deliberate design. Atlas does not have that quality. Its geometry is too clean, its symmetry is too precise. It occupies an uncanny valley between the natural and the artificial, close enough to each category to be mistaken for either, belonging fully to neither in visual terms. But it belongs entirely to one of them in scientific terms. Atlas is natural. Every gram of its ice arrived through a process that required no planning, no intention, no awareness. The rings did not decide to build a saucer-shaped moon. Saturn's gravity did not aim ring particles at Atlas's equator with purpose. The Lagrange point gateways that funnel material onto the moon are consequences of orbital mechanics, not engineering. The flatness of the ring plane that restricts delivery to a single latitude band is a result of collisional damping, not design specification. There is no blueprint. There is no architect. There is only physics, operating within a specific set of boundary conditions, producing an outcome that happens to mimic the aesthetic of intentional construction. This is not the first time the solar system has produced something that looks designed. It may not even be the most dramatic example, but it is among the most visually striking. And it carries a lesson that extends far beyond one tiny moon, orbiting one ringed planet. The lesson is about the relationship between environments and the objects that form inside them. In most of planetary science, we think of moons and planets as bodies shaped primarily by internal processes. Earth's continents move because of mantle convection beneath the crust. Mars's volcanoes grew because of magma rising from the interior. Enceladus's plumes erupt because tidal heating from Saturn warms a subsurface ocean. The emphasis is on what is happening inside the world. The environment, the space around the body, is treated as a passive backdrop, a cold vacuum through which the world moves without being fundamentally shaped by it. Atlas inverts that assumption completely. Atlas is a body shaped almost entirely from the outside. Its internal processes contribute nothing to its current form. There is no geological activity, no convection, no tidal heating significant enough to alter its structure. The core sits inert and cold beneath the ridge, contributing only its mass and its gravitational field. Everything that makes Atlas visually distinctive, the ridge, the disk profile, the smooth equatorial band, was imposed by the external environment. The rings reached out and built those features onto a body that could not resist them and could not erase them afterward. This makes Atlas something rare in planetary science. It is a moon that records not its own internal history, but the history of the system it inhabits. When scientists study the shape of Mars, they learn about Martian geology. When they study the shape of Atlas, they learn about Saturn's rings. The moon is a sensor, a three-dimensional detector that captured the physical conditions of its orbital neighborhood and preserved them in its own body. The flatness of the ridge encodes the flatness of the rings. The porosity of the ridge material encodes the gentle velocity of accreting particles. The asymmetries in the ridge encode the orbital eccentricity of the moon and the density profile of the ring edge. Every feature on Atlas is a measurement of something that happened in the space around it. This idea that a small body can serve as the fossil record of its environment has implications beyond the Saturn system. It suggests a way of reading landscapes that planetary science is only beginning to develop. If a moon near a ring system can be physically sculpted by that system, then what other small bodies in the solar system carry the imprints of the environments they formed in? What can the shape of an asteroid tell us about the protoplanetary disk it grew inside? What can the surface of a comet reveal about the conditions at the outer edge of the solar nebula 4.5 billion years ago? Atlas demonstrates that small bodies are not just inert rocks drifting through space. They are documents, texts written in shape and density and surface texture, carrying information about places and times we cannot visit directly. Those fingerprints come from two entirely separate sources, each leaving its mark on a different part of the moon's body. The equatorial ridge, the younger surface on Atlas, the region most recently refreshed by incoming ring particles, carries a faintly reddish tint. That color comes from a chromophore, a light-absorbing compound embedded in Saturn's ring material whose exact chemical identity remains a matter of active investigation. Candidates include complex organic molecules, nanoscale iron particles, or some combination of both. Whatever it is, this reddish agent pervades the main rings and stains anything that accretes from them. The ridge is tinted because it is made of ring material, and ring material carries this color with it. The polar regions tell a different chemical story. Above and below the equatorial belt, on the older core surfaces that have not been resurfaced by ring accretion, the ice is brighter and cleaner. This brightness comes not from the rings, but from Enceladus, the geologically active moon orbiting farther out in the Saturn system. Enceladus's south polar geysers eject plumes of water vapor and fine ice grains into space at velocities high enough to escape the moon's gravity entirely. That ejected material feeds Saturn's diffuse E-ring, a broad, tenuous band of microscopic ice particles that extends across much of the inner satellite system. Over time, those E-ring particles settle onto the surfaces of nearby moons, depositing a layer of fresh, bright water ice. On Atlas's poles, where ring accretion does not continuously deliver new reddish material, this Enceladus-sourced frost has accumulated largely undisturbed, creating surfaces that are measurably brighter and spectrally cleaner than the equatorial ridge. The result is a moon wearing two coats of paint, applied by two completely different processes operating at two completely different locations within the Saturn system. The equator records the chemistry of the ancient rings. The poles record the volcanic output of a moon hundreds of thousands of kilometers away. Atlas does not merely sit inside its environment. It absorbs information from multiple directions simultaneously, recording the chemical signatures of processes that have nothing to do with each other except that both happen to leave traces on the same small body orbiting at the boundary of Saturn's rings. There are unresolved questions surrounding Atlas that keep the scientific conversation active. That same 2024 review by Nicholson and colleagues highlighted several open problems that future research or future missions may need to address. One of the most fundamental is the question of age. How old are Saturn's ring moons? Are they ancient, forming alongside the rings early in the Saturn system's history? Or are they relatively young, assembling from ring material that was itself produced in a more recent catastrophic event? This question connects to a broader debate about the age of Saturn's rings themselves. For decades, the rings were assumed to be primordial, as old as Saturn, roughly 4.5 billion years. But measurements from Cassini's final orbits, during which the spacecraft flew between Saturn and the inner edge of the rings, produced a mass estimate for the ring system that was surprisingly low, equivalent to only about 40% of the mass of Mimas. That low mass, combined with the measured rate at which ring material darkens over time from meteoritic contamination, led several research teams to conclude that the rings may be much younger than the planet, perhaps only 100 million to 200 million years old. If the rings are young, then Atlas and Pan and Daphnis may also be young. Their ridges, in that scenario, would not have been accumulating material for billions of years, but for perhaps a few tens of millions. That timeline changes the character of the story without changing its mechanics. A young Atlas is shaped by the same process as an old Atlas. Ring particles still accrete onto the equator. The geometry is still enforced by the thinness of the disk. The result is still a saucer-shaped moon. But a young Atlas implies that the ring sculpting process operates on timescales short enough to produce dramatic results within a small fraction of the solar system's age. It means the rings are not a permanent fixture but a transient phenomenon, and the moons embedded within them are transient too, products of an environment that will not last forever. The rings are slowly losing mass, draining onto Saturn through a process called ring rain, where charged ice particles spiral inward along the planet's magnetic field lines. If this process continues, Saturn's rings may largely disappear within the next 100 million years or so. And when the rings go, the sculpting process that shaped Atlas goes with them. No more equatorial accretion. No more ridge building. Atlas will continue to orbit, carrying the form the rings gave it, long after the rings themselves have vanished. It will be a monument to a system that no longer exists, a shape that preserves the memory of the environment that created it. Whether the ring moons form a long-lived population or a transient one remains contested. The Nicholson review noted that some models suggest the moons could be continuously created and destroyed, ground down by meteorite impacts and rebuilt from the resulting debris, cycling through generations of formation and destruction on timescales of hundreds of millions of years. In this picture, the Atlas we see today may not be the first Atlas. It may be the latest in a long lineage of small moons that formed at the A-ring edge. Accreted equatorial ridges were eventually shattered by a large impact, and were then replaced by a new body assembling from the wreckage. Each generation would carry the same saucer shape, because each would form under the same set of conditions. The form is not a property of any individual moon. It is a property of the location. That thought is worth sitting with. The saucer shape of Atlas may be less like a fingerprint, unique to one object, and more like a uniform, worn by whatever body happens to occupy that orbital slot at any given time. The ring edge at 137,700 kilometers from Saturn is a sculptor's studio, and whatever raw material passes through it gets carved into the same basic form. The rings do not care what the seed body looks like when it arrives. They will flatten it, coat it, build a ridge around its middle, and send it on its way looking like nothing else in the solar system. There is something almost industrial about that image. A location in space that processes raw material into a specific shape, repeatedly, automatically, without oversight. It is an assembly line operated by gravity and geometry alone, producing objects that look manufactured because the process that creates them is, in its own way, a kind of manufacturing. Not intentional manufacturing. Not manufacturing with a goal or a blueprint, but manufacturing in the most fundamental sense of the word. The making of a form through the repeated application of the same forces to the same material under the same conditions. And here is where the story of Atlas arrives, at the thought that makes it genuinely significant beyond planetary science. We live in a universe where the line between natural and artificial is drawn by a single criterion: intention. A bridge is artificial because someone meant to build it. A canyon is natural because no one did. The materials are the same, the physics is the same. The difference is entirely about whether a mind was involved. Atlas challenges that distinction, not because it was designed, it was not, but because it demonstrates that undirected physical processes can produce results that are visually indistinguishable from the products of design. The saucer shape is not evidence of intelligence. It is evidence that the universe's own machinery, operating without awareness, without goals, without any concept of what it is producing, can generate forms that a mind would be proud to claim. This has consequences for how we think about the search for artificial structures in the cosmos. Astronomers looking for evidence of extraterrestrial engineering sometimes search for objects or signals that appear too orderly, too geometric, too structured to be natural. A perfectly regular signal might indicate a transmitter. A star dimming in a pattern might suggest a megastructure. An object with an impossible shape might hint at construction. Atlas reminds us to be careful with that logic. Nature is capable of producing objects that look constructed. The equatorial ridge of a tiny moon orbiting at the edge of Saturn's rings is as geometrically precise as anything a civilization might build, and it was built by ice grains drifting onto a surface under almost zero gravity. If Saturn can produce a flying saucer without trying, we should be cautious about concluding that any strange shape we find elsewhere in the universe must be the work of a mind. At the same time, Atlas enlarges our sense of what the universe can do without help. There is a tendency, deeply human and entirely understandable, to assume that complexity requires a creator. That order implies intention. That geometry demands a geometer. Atlas says otherwise. Atlas says that the right combination of simple forces, operating under the right conditions for the right amount of time, can produce something that looks for all the world like it was planned. And it was not planned. It was not even aimed at. It simply happened. The way crystals happen. The way river deltas happen. The way the spiral arms of galaxies happen. Order emerging from the blind operation of physical law. When you look at the Cassini images of Atlas, what you are seeing is not an anomaly. It is a demonstration. A demonstration of what the solar system is capable of producing when gravity is weak, ring material is available, orbital geometry is flat, and time is long. You were seeing a moon that was sculpted by its own environment into a shape that challenges your intuition about what nature can and cannot do. You are seeing a world that looks like it belongs on the cover of a science fiction novel, floating serenely in the blackness near Saturn's rings, as real as the ground under your feet, and as strange as anything human imagination has ever conjured. Atlas is approximately 41 kilometers wide. It weighs less than a large terrestrial mountain. It orbits Saturn once every 14 hours and 24 minutes, tracing the same path it has traced for longer than anyone can say with certainty, locked in synchronous rotation so that the same face always points at the planet that dominates its sky. Its equatorial ridge wraps broadly on either side of the midline, a belt of fine-grained ice deposited from the material of Saturn's A-ring. Its poles are rougher, older, more battered. Its interior is mostly empty space, a fragile accumulation of frost and void, held together by forces so weak that a child's throw could escape them. It has no atmosphere, no magnetic field, no internal heat, no geological activity of any kind. It does nothing. It simply orbits, and in orbiting, carries the shape that Saturn's rings imposed upon it, like a mask it cannot remove. And that shape is a flying saucer. Not because aliens built it, not because the universe has a sense of humor, not because there is some hidden message encoded in the geometry of a 30-kilometer ice disk orbiting a gas giant 800 million miles from the nearest classroom where someone might learn about it, but because the universe is a place where the simplest forces, given the right stage, can perform extraordinary acts of construction without knowing they are building anything at all. The rings of Saturn did not set out to create something beautiful. They did not intend to produce an object that would one day stun a room full of scientists, staring at a photograph transmitted across 1 billion kilometers of empty space. They simply operated. Particles collided, orbits circularized, the disk flattened, material drifted, gravity captured it, the equator received it, the ridge grew, and the result, after all that blind, patient, purposeless work, was something that looks like it was made. That is the deepest lesson Atlas has to teach. Not a lesson about Saturn, or about ring physics, or about the taxonomy of small moons. A lesson about the universe itself, about its capacity to surprise, to produce structures that exceed our expectations of what nature should look like. To generate beauty and precision and geometric elegance from nothing more than the relentless application of a few simple rules to a few simple ingredients over a span of time we can barely comprehend. Atlas is not a spacecraft. It is not a relic of some vanished intelligence. It is not evidence of anything other than what it plainly is. A tiny moon, made of ice, living inside a ring system, shaped by the only forces available to it, carrying a form that will endure long after the rings that created it have drained away into Saturn's atmosphere and vanished. When those rings are gone, Atlas will still be there, orbiting in silence, still shaped like a disk, still carrying the ridge that the rings built for it, a fossil of a system that no longer exists, a shape without a sculptor, a monument with no architect, a flying saucer made of frost, circling a planet in the outer darkness, as natural as gravity and as strange as anything the human mind has ever tried to explain. The solar system built this, not for anyone, not for any reason. It built it the way it builds everything, by following the laws of physics wherever they lead, even when they lead to something that looks impossible.